Hello friends, this is Mr. Sarvesh Varjurkar. We are here for the session organized by Ballarpur Institute of Technology, Ballarpur under AICT sponsored Prerna scheme for SC/ST students. Today's session is our session number 13, in which we are going to see about the our subject algorithm, where the topic that we are going to cover it today is graph and graph traversals. Firstly, we'll go with the data abstractions and what are graphs and what we are going to cover it in today's video. I'm going to explain it. Less generalized data structure and ADTs, that is abstract data type. More on algorithms and related problems that require constructing data structure. See, it's belong to non-linear type of data structure. As we know that there are two different types of data structure. One is linear, another one is non-linear, in which in linear we are always very much familiar with the stacks, queues, linked list, etc. In non-linear there are basically we are divided it into two major parts. One is trees and another one is graph. And it requires the data structure that makes the solutions very efficient. Topics that we are going to cover, that is majorly it is graph. So what is graph? The normal definition of graph is like a graph is a formalism for representing relationship among the various atoms. Like a very general definition or very general concept, in the diagram you are looking on the right hand side is the diagram of normal vertices and edges. The vertices that we are always used the vertices that we are going to show it with the help of nodes or with the help of that circles, and the link between the two circles or the two nodes are called as edges. A graph is a pair, that is G of V comma E, where a set of vertices which are also known as nodes, and we are generally representing it by V, that is V1, V2, V3, Vn up to so on. A set of edges is like age 1, age 2, age 3, age 4, age 5, and so on. In the given diagram over here, there are three different edges. Each edge is a pair of vertices. Of course, that is a connection or that is the link between the two nodes, and edge connects to the vertices. And yes, there are two different types of graph. One is directed graph and another one is undirected graph. What is the difference between the directed and undirected graph? The directed graph, where there the edges are connecting, are having the direction with them, called as directed. If the edges does not have directions, we'll simply call it as the undirected graph. Next, we can think of the graph as an abstract data type first, where operations would include is age, that is Vj and Vk, but it is unclear that standard operations that would be for such as an ADT, that is abstract data type. Instead, we tend to develop algorithms over graph, and then we are using the data structure that are efficient for those algorithms which we have already been used over here. Many important problems can be solved by formulating them in the graph in the terms of graph, and by applying a standard graph algorithm. There are various different algorithms, those who are completely based on that graph. And next is some of the graphs that we are some of the examples, or where the vertices and what are the edges are the very best example, like web pages with link, Facebook friends, that is a complete structure. If you see the main window of the Facebook, it shows it with the connecting vertices from the various countries from where we are connected in the world, and the nodes are nothing but the countries, and the link to connect between them are nothing but the edges over there, where we know that input data methods in a program that can call each other, road maps, airline routes, family trees are nothing but the or course prerequisites as well, in a very realistic word, course prerequisites. We know that the hierarchy, if you know the C language, you are able to know the next language, that is C++. which we are going to know with the basic and with the upgraded versions of every different languages. That is a hierarchy or prerequisites, I can say. Graph are a powerful representation and that have been studied deeply. Graph theory is major branch of research in combinatorics as well as in discrete mathematics. Next, in terms of mathematical, graph can be represented in data structure, so that we can represent a graph by using an array of vertices and a two-dimensional array of edges as well. Before we proceed further, there are various terms that we are very much aware, or we need to very much aware about all the terms of the graph. Firstly, we'll see about that undirected graph. What is undirected graph? Where their edges have no specific direction. See, over here there are four different nodes or four different vertices, say A, B, C, and D, and four different edges over there: A to C, A to B, B to C, and C to D, like this. But this is a undirected graph. Why? We can connect from A to C, as well as we can definitely connect from C to A. Edges are always two-way connection between the nodes in undirected graph. Thus, only one of these edges need to be in the set. Rest other is implicit and so normalize how you check for it a degree of a vertex and the number of edges containing that vertex. What is that degree? For example, number of edges containing that vertex is the degree of that node or degree of that vertex, I can say. For example, see A are having connected with containing two different vertex, like the degree of the node A is 2. Same thing, degree of the node D is 1, degree of the node B is 2, C is 3, like this. In a directed graph, the another way is a directed graph where edges have direction. That is the only difference between directed and undirected itself. So we can call the source, that means from where the direction initiates, from where the edge initiates, called as the source, and where the edge targeted is nothing but the destination. Or in other words, we can say that in degree and out degree of vertex. In degree is nothing but the number of inbound edges or the number of incoming edges on a particular node, called as in degree of a vertex. Like in the first diagram, I can say the number of in degrees of A of the vertex A is 1. Only one node is only one node, one edge is pointing towards A. That's why we called it as the in degree of A is 1. In terms of B, there are two different edges are connecting with B or coming towards B. That's why the in degree of B is 2. Likewise, in contrast with that, out degree can also be called calculated. Out degree of a vertex is nothing but the number of outbound edges, where edges where the vertex are is the source itself. Self edges unconnected connectedness is nothing but again the different part, where self edge is also known as the loop edge, where it starts from the same vertex and ends on the same vertex continuously, like this. No self edges, some self edges and all self edges. There are such type of graph can also be in there. A node can have a degree, in degree and out degree of 0, of course, and graph does not have to be connected. If I can say, if I am going to explain it with the help of a single node, it can be in degree is 1, out degree is also 1, and node is also 1, edge is also 1, like this. If you are using like that self edges, more discussion is not that much important on that topic, so we'll leave it at. Next is more notations are vertices and edges. As we know that maximum for undirected, maximum for directed is like this. And majority of the times in the gate examination, the question on that topic are frequently been have frequently been asked. Like if you are given a graph with you, a normal graph, or it may be directed, it may be undirected, and there are 5 to 6 different number of questions that are asked in that related to that particular graph for 1 mark. The questions are: what is the in degree of every vertex? What is the in degree of the vertex A, B, C, like this? Along with what is the out degree of the vertex B, C, D, like this. If you are imagining it with the diagram of say 8 different nodes, and from that they can ask randomly. And uh, the degree of the tree, degree of the node, degree of every vertex, and so on. It might be asked to you. Number of vertices, number of edges, that may be the question, and respective answers will be there as a part of options. From that, you have to choose in a proper sequence and proper as the answer in the gate examination. Which would the question again? There are which would use the directed edges, which would have the self edges. Self edges, I can definitely say in NFA. When we are going to cover the topic related to your theory of computations, that NFA majoritarily having that self loop called as self edges, where the degree could be 0 and degree are like this. So these are the various examples that we have already been weighted aware. And next is the weighted graph. There are various different types of graph: weighted graph, unweighted graph, directed graph, undirected graph. As the name suggests, it is weighted. Weighted means when there is a connection between two different nodes, if that age is having if that age is having any different value as a weight over there, any different value as a weight over there, that value is called as weighted, or weight of that age. That value is called as the weight of that age. I repeat. Then there is one more terminologies which we are frequently using in this. That one is age. As we know that age represents a path between two vertices in a line, and between two vertices. In the following example, say Clinton and Mukil Mukil Cho, Mukilto, that they are connected with the help of one age, and that age is having the value say 20. It may be of any unit. Then there are orthogonal, or whether the graph is directed. Some graph allows negative weight, many of them are does not carrying the negative weight, and so on. So this is all about the weighted graph where the age is having any weight with them. Path and cycle. The path is represent a sequence of edges. Very simple. Path represents a sequence of edges between the two vertices. In the following example, say one path, like I can say it's from Seattle, Chicago, Dallas, San Francisco, and Salt Lake City. It is a complete connected path which starts from the Seattle and ends on the Salt Lake City, like this. It may be any different path you can change. You can see it is a complete connected graph. So you can change the path, you can change the way, you can change the track. Everything is possible over there. So a cycle is a path that begins and end at the same node. See, in the path I have started it from Seattle and ends on Salt Lake City. Whereas if I am going to deal about the cycle, I need to start from the I need to start from any vertex, and I should end on that vertex itself. If I start from any vertex and end on that particular vertex itself, is called as the cycle of the cycle. I can say like it's a normal cycle. Path length and number of edges in the path, and path cost is the sum of weight of each edge over there, where p is equal to the path, like this, and length is say 5, and length is for cost for that particular length to cover all the cities is like 11.5 in this particular way. From which I can, if I start with Settle, then set Salt Lake, then Chicago, then Dallas, then San Francisco, and at last again that Settle. So this particular complete path is nothing but a cycle which cost while visiting or while traversing this particular path or cycle, it requires me around 11.5 as a traversing cost in between them. Simple path and cycle yet repeats no vertices, where except the first might be the last. It can be any different path. I can say like Seattle Salt Lake City, San Francisco, Dallas. That is one path that can start from Seattle and ends on Dallas. Again, second path, like if I want to visit again that city, that may be there. And cycle, that is a path that ends where it begins. As simple as that can. Path, a cycle is a path that ends where it begins. That's it. A simple cycle is a cycle and a simple path. It starts from the city and ends. Start from the city where it begins, ends from the city where it begins as well. Uh, this is all about the simple cycle. We are aware about it. Next, path and cycles in directed graph. Is there a path from A to D? No, no any direct path is there. We cannot reach to D in terms of that directed graph. Since we can reach from A to B and B to C, but we cannot reach to D. The reason is having that, the reason is D does not have any inward arrow or any inward edge towards itself, towards himself, in which I can say that A to B, B to C is a path, or I can reach from A to the node C, but I cannot reach to the node D. So answer is no. Does the graph contain any cycle? Yes, the graph contains any cycle. Isn't it? Yes or no? No. There is the graph does not carry any cycle. Since it can reach from the node D to B, it can reach from the node B to C, but there is no any arrow from outward arrow from C, and there is no any inward arrow towards D. So there may not be any there is this particular graph does not contain any cycle. So answer is no, and answer is no for the same. Undirected graph connectivity is like undirected graph is connected if for all the pair of vertices u where u is not equal to v, there exists a path from u to v, where the connected graph and the disconnected graph are like this. Disconnected graph, if there are no any connection between all the edges, sorry, between all the vertices, and in connected graph there is somewhere it is connected to any different node to all the nodes in the graph, called as connected graph as well. An undirected graph is a complete or fully connected if for all pair of vertices where u is not equal to a, there exists an edge from u to say v. Number of edges are not equal to number of vertices, then there exists an edge from u to v itself. So these are the connected graph, disconnected graph, and fully connected graph, where all the edges are connected. Sorry, all the different nodes or vertices are connected with each other. In that case, I can simply say in the given diagram, which is at the corner of the screen, bottom corner of the screen, bottom right corner, every node is connected with every other node. You can see, you can check, you can select randomly any node, and I can say like it is a completely or fully connected graph with the other nodes. See, if you are consider this is connected with this, connected with this, connected with this, as well as this. Same thing, you can choose any different node randomly, and it may give you the fully connected graph. Directed graph connectivity, a directed graph is a strongly connected if there is a path from every vertex to every other vertex. A directed graph is weakly connected if there is a path from every vertex to every other vertex, ignoring the direction of the edges as well. In the diagram, it is already been there. The directed graph is a complete or fully connected if for all the pairs of vertices, say u is not equal to v, there exists an edge from u to v. If there is any edge from u to v, that there is a direct graph which is completely or fully connected if all the pairs of the vertices where u is not equal to v, that means number of edges are not equal to number of vertices, there exists an edge from u to v in that case. So this is a directed fully connected graph is also been there. So for undirected graphs, they are connected. For directed graphs, they are strongly connected or weakly connected. That may be the question. So it depends up to the way of up to the diagram, which is up to the graph which is given to you itself. When talking about the graphs, we say that a tree is a graph. A tree is also with a graph on the given diagram. In the given diagram, if you look critically, it seems like a tree where D and E are having one children, say B is having another one children, A is having children, C is having children, F, and F is having again F is having again two children, say G and H. In terms of tree, it is very fine. But in terms of graph, it is an undirected graph. It is an undirected acyclic graph where the nodes are connected. Yes, very important line. I am mentioning one question came on this particular line. On this particular line in some of the previous gate paper for true or false type of question. The question was like all the trees are graph, but not all graphs are trees. I repeat, all the trees are graph. Every tree is graph, but not all graphs are trees. Is it true or false? It is absolutely true. It is absolutely true. How does this relate to tree? That we know that we know and love about the scene. Cause a tree can be the graph, or tree should be the graph, but not all graph are trees. Not all graph are trees. So we'll see in that matter again. We are mostly accustomed to rooted trees. When we have studied that trees in the data structure, that accused to rooted trees where we identify the unique root and we think that edges are directed and parent to children. Just now I have explained like this. So picking a root gives a unique rooted tree. You can pick any different node as a root, and the tree is simply drawn differently with undirected edges like this, which I have already been drawn in the given slide. But in a directed way, the trees are not unique. So picking a root gives you a unique rooted tree, and a tree is simply drawn differently and with its undirected edges. That is again fine. If I starts from say F, I can definitely able to draw the tree since F is connected with three different edges. Sorry, three different nodes like G, H, and say C. And C is connected to A is connected to B is connected to two different edges, that is D and E. So I can definitely draw a tree from the given graph. That's why I have mentioned one thing. All trees are graph. Remember this thing. All trees are graph, but not all graph are trees. Yes, a DAG, that is directed acyclic graph. What is that DAG? A DAG is a directed graph with no directed cycles. Every rooted directed tree is a DAG, but not every DAG is a rooted directed tree. I repeat, every rooted directed tree is a DAG, but not every DAG is a rooted directed tree. So every DAG is a directed graph, every directed acyclic. I repeat, the word is very important. Acyclic, where there is no any cycles are present, called as acyclic graph. And but not every directed graph is a DAG. So this is all about the DAG. There are various examples that we are seeing it from the very first slide. Density and sparsity of a graph of a directed and undirected graph can be calculated like this. In a undirected graph, it can be recalled like where the number zero is less than equal to edges is less than equal to vertex to the power 2 mod. Everything should be positive, right? So in directed graph, 0 is less than or equal to e is less than or equal to v to the power 2, where e stands for edges and v stands for vertices. So for any graph E is order of v to the power 2. Another fact is like if an undirected graph is connected, then the edges are greater than or equal to v minus 1. There is one different principle which is not in your gate syllabus, named it as pigeonhole principle. So that sparse matrix and density can be calculated over there, where ages is often much smaller than its maximum size, and we do not always approximate as e, that is ages as order of v to the power 2. No, there is a correct bound, but often not tight as well, so it may be up to the upper bound over there. So this is all about that density and sparsity of that thing. Next is adjacency matrix, where adjacency matrix, where it is assigned to each node a number from 0 to v minus 1. V multiplied by v matrix of booleans, it is 0 or 1 itself. Then m of u comma v is equal to true. That means there is an edge from u to v itself. Like this. See, where there is a 0, where there is no any edge, we can say it as a false. Where there is a edge from that node to the given node or to the directed node, we'll say it as it is a true in terms of that adjacency matrix. Look like this: a to a, row and column wise I have mentioned a b c d, the four nodes, and column is like again a b c d. So a to a, there is no any node, so that's why I have mentioned f over there in that adjacency matrix. A to b, one node is there, that's why I have mentioned 2, I have mentioned t. Only one is there from a to b, rest all are false. Same thing is with b. B to a, there is one edge is present, that's why I have mentioned b to a is t, and rest other nodes from b to b, c and d are false. Likewise, there are certain properties while running this adjacency matrix. There are certain properties, and the properties I have mentioned over here. One is running time to get a vertex, that is out edges, and gets a vertex in edges, that can decide if the edges exist. If the edges are exist over there, then insert an edge again, and delete an edge is also been possible. Space requirement, it is based for sparse or dense graphs, where the graph the length of the graph or the edges and the edges along with the vertices in the graph are much more with high density dense graph. In that case, this adjacency matrix really plays a very vital role. The space requirement, the memory requirement, the space complexity for the adjacency matrix in the given graph is like order of v to the power 2. Based for sparse or dense graph, it is definitely for dense, as I have just now mentioned the things. The properties of that adjacency matrix are like this: will be symmetrical, they will be symmetric about all the diagonal axis. Matrix could we have space by using only about half of the array, but how would you get all the neighbors? So it is quietly next to impossible. So how can we adopt the representation for weighted graphs? Instead of boolean, we can store a number of every is not the number of each and every cell instead of boolean graph. And next is, simply when we are going to deal with the boolean, it really requires some value to represent, that is not an age. It may be 0 minus 1 or some other value which is based on how you are using the graph. It might need to be separate field, or if no restrictions on weights, and it can give you the adjacency list like this, that can assign the node from number 0 to v minus 1, and an array of length v in which every entry stores a list of adjacent vertices. Example, in the linked list, we know that in the linked list that nodes are carrying the values with them, and the pointer, that means the edges, are connected, they are having the address of the next location itself, so that it can get a vertex of out edges, it can get a vertex of in edges, decide if some edges are exist or not. Insert, that means addition of a new edge can also be possible. Removal of any edge is again been possible, same as like as we have done it in the linked list itself. The space requirement, it may be best for sparse matrix, again adjacency list, and see, get a vertex of out, that is order of d, where d is the out degree of the vertex. in degree order of E, where it could keep a second adjacency list for this, decide where some edges are exist or not, where D is the out degree of the source, unless you need check if it's already been there, and where the D is the out degree of the source or not. In that case, space requirements are like order of V plus E, the total time complexity, sorry, space complexity order of vertices plus edges. Now again, that undirected graphs in terms of adjacency list also work for undirected graph with some caveat, uh, where we can put the edge in two lists to support efficient get all the neighbors. And the question, that is a very diplomatic question, I can say, which one is better? Graphs are often sparse, yes, street from grids, and airlines rarely fly to all the cities. Adjacency list should generally be your default choice. Slower performance compensated by greater space saving. So this is all about that graph. Now come to the topic, that is graph traversals. For an arbitrary graph and a starting node V, find all the nodes those who are reachable from V. That is, there exists a path where possibly do something for each node, where we can print to output, set some field, return from iterator, etc. Some related problems are like, is an undirected graph connected? Is a digraph is weakly or strongly connected? For strongly, there is a need or there is a need of a cycle that can back to the starting node. And basic algorithm for traversals is like, select the starting node, make a set of nodes that can adjacent to current node, visit every node in the set, but mark each node after visiting them, so you don't revisit them and eventually you need to stop. It directly means that there is no any need to visit a node again, I mean twice. Repeat above steps, but skip marked nodes. There is no any need to visit the visited nodes again, since it requires the running time, that is options, running time and various options of that. So assuming and add and remove are order of one, entire traversal is order of ages. If we are using an adjacency list, the order that we traverse depends entirely on how add and remove work are implemented. DFS is a stack that depth first search, and DFS is a queue where breadth first search can be there. These are the two major traversing techniques of a graph, where depth is nothing but a recursively explore one part before going back to other, and where other parts are not yet explored. And breadth are nothing but the explore areas closer to the start node, those who are very adjacent to every layer by layer, or order, sorry, level by level, called as that breadth first search. Recursive DFS is like example with a tree. A tree is a graph, and DFS and BFS are particularly easy to see in one. You can see like this is a graph where A is connected with B, C, and B is connected with D and E, where C is connected with F, F is connected with G and H. It is already been directed. So DFS node starts from the root itself, and it can directly reach to the end first, like A, B, to the depth of the tree first. A, B, C, sorry, A, B, D, and then from D it can back towards B, since it have visited D, and then it can back towards the B, and from backtracking I can say, and from that B it can again visited the unvisited node from that given node. Then it reached to E, left hand side is completed, then it come backs to B, again B come backs to A, and on the right hand side it now visited with C, C is connected to F, F is connected, after F it is connected, it is going to deal with G, or it can visit or scans the node G, and after G it can come back to F again, and F to H again, like this. But F is already been visited, so there is no any need to again put that element into the stack. This is a pre-order traversal. DFS is always called as a pre-order traversal of the trees. The marking is unneeded here because we support arbitrary graphs, so we need a means to process that each node is exactly, we are visiting exactly once. DFS it with the stack. The example of the stack is like first in first out. The element which visited first should be entered in the stack first, and then the same example is like A B D E C F G H like this, and order process is like A C H G B E D, a different order but still a perfectly fine traversal for the graph. Like A to C, on the right hand side it had taken as a depth first, so it doesn't matter. A C F and F and H, it is the extreme depth of the tree on of the given graph on the right hand side. A C F H, and from H it can take a backward way, F, unvisited node, that is G, and again come back to F, again come back to C, C to A, where all these nodes are already been visited, and then B. Then the extreme depth of B is, it may be E, it may be D, doesn't matter. So we'll go with E and D, nothing but the same. BFS can also be solved with the help of Q as well, where A to B, B to C, and can be there. Uh, the level order traversal also. A small comparison. In brief, I'm going to explain it in detail after this some of the slides. With the help of one normal example, I'm going to explain it how the traversal, that is the BFS breadth first search, can be applicable or can use. I can definitely show it after few slides. BFS always find the shortest path. Some of them from the starting node to the target node, where the storage of the BFS can be extremely large. A canary tree, where the canary tree or binary tree of a height h can also be result in the q size of k to the power h, if the height of the tree that sorry if the in the way that the tree is been distributed, maybe the high to the power of that height will be the height could be h, will be the result in the q size of that tree. DFS can also use less space in finding the path. If long path in the graph is P and highest out degree is D, then DFS stack never have more than D multiplied by P elements. So next is iterative deepening. Again, the next part of that depth first search, iterative depth first search. N number of times that iterations may occur in the, while searching any node in the graph. Like BFS, IDFS finds the shortest path as well, and like DFS, IDFS use less space. Some work is repeated but minor compared to the space savings can also be possible in terms of that iterative deepening. It can also be there to use to save the path, where our graph traversal can answer by reachability question, and it's very easy. Simply like this, it in the given example, write the path from Settle to Austin. Remember, mark nodes are not re-encaved. We can need to find the shortest path. That may not be unique. You can start it from, say, unless and until it is the unweighted graph. So we'll go with any different path like this. And it is possible to visit any different node from any different city as well. So if I starts from, say, Austin, I can go to Dallas. From Dallas, can go to San Francisco. From San Francisco, I can go to Seattle. Another path, Dallas to Salt Lake, and Salt Lake to Seattle. From Chicago again, I can directly go to the Seattle. One and the same thing. Whichever which gives me the shortest path from the given directed node, or the given weighted directed graph, I can choose that particular path to find the shortest path in the given problem, in the given diagram, or in the given graph. Given a DAG is like G of vertices and edges, that graph is nothing but a combination of vertices and edges, where all the outputs of the all the vertices in order such that if no vertex appear before any other vertex that has an edge to it. In this given way, the prerequisites has been given over there in terms of CSE. CSE, 142. It goes with 143. It directly means that for the subject 143, prerequisites are Math 126 and CSE 142 for the subject 143. And if you have studied 143 properly, you can able to go with four different subjects like CSE 331, 311, 341, 351, and so on. Likewise, the complete hierarchy or a tree is been get justified, is been get followed in terms of that topological sorting of a graph. In terms of output, I can say 142 to 120, 142 comma 126, 143, 311, 331, 332, 312, like a particular track, 341, 351, 333, and 33, and 440 and 352. 440 is also connected. Look like this. 440 is also connected from the 2333 as well. So disclaimer is not like, do not use it for official advising purposes. It is normal example. So don't worry about it. And next is terminologies that we are using in DAG that represents a particular order and a topological sort that produces a total order that is consistent with it. Why do we perform the topological sort? The answer is because the cycle means there is no any correct answer, since I can visit n number of time a particular node. Because since if the cycles are there, so I can visit with the help of that ages from one city to another city again and again. So if cycle permits it, it does not give a proper answer. Uh, is there always a unique answer? The answer is no. There can be one or more answer depending on the provided graph, since you can choose arbitrary node while traversing in the graph. There is no any prerequisite or predefined things that you have to choose root node first, you have to choose node number one first, alphabetical order. No, you can go with any different way. Why DAGs have exactly one answer? It is say that it is the featuring of how to finish your degree, computing the order in which recalculate the cells in the spreadsheet, and so on. In general, we can use dependency graph to find an allowed order of its execution. This is all about, see, if remove edges are there in the given example, I can say like in degree of every node, say 126 is 0 because there is no any inward arrow towards 126. In degree of 142 it is 0, 143 it is 2. The reason 143 is having two receiving two different arrows from two different positions. 311 can go with 311 only one in degree, 312 2 in degree, 3311 3321, 333 is 2, 341 is 1, 351 is again 1, 352 is 1, and 440 is also 1, since it is having only 1 degree towards them. In that case, the output will be 126, 142, 143, 311, 331, since it is having 1 in degree, and 331 is having only 1 in degree towards itself. Then 332, then 312, since it can connected with three different nodes. 332 is having three different out degrees. One is going to 440, another one is going to 312, another one is going to 333. So we'll keep it in that particular manner in terms of breadth first search, and then 351, 353, and so on, like this. This is the worst case running time complexity. It is initially it is order of vertices plus edges. Sum of new find new vertex, that is order of v to the power 2, and sum of decrements is order of edges. So total is order of vertices square plus edge. That is not good for all the sparse graphs accordingly. It is doing better, so you are able to find it out the queue with the help of queue and some more graph algorithm that can you are able to find it out with what happens with that we consider with the weighted edges. And next time we'll discuss the shortest path algorithm if we have scheduled that particular lecture in the upcoming days. Now we'll actually enters in that breadth first search, how it works. Answer is the explanation is very simple, which I'm going to give it to you with the help of one diagram, with the help of graphics as well. This is the simple outline of breadth-first search, which we are going to cover the various topics in breadth-first search. What is breadth-first search, the necessary terms, and BFS illustration with the example pseudocode algorithm, applications, space complexity, time and space complexity, and conclusion. See, the inventor of BFS is like Konrad Zuse, where he was a German civil engineer and inventor of computer pioneer. His greatest achievement was the world's first programmable computer. The civil engineer person, German civil engineer person, Mr. Konrad Zuse, have developed first programmable computer. By applying this breadth first search, where breadth first is an algorithm for traversing or searching the tree and the graph as a data structure. It starts at the tree root and some arbitrary node of the graph. It can be any different node from the given graph. Sometimes it referred to as a search key and that explores all of the neighbor nodes at the present depth. It is prior to moving all the nodes and at the next depth level itself. So why should we know about that BFS? The graph consists of vertices and edges, where V is the set of edges and V is the set of vertices and E is the set of edges. A tree is a collection of entities called nodes. You know that tree is a directed tree. Nodes are connected by edges, and each node contains a value or data. It may or may not have the child nodes. For example, node number 1, 4, 7, and 10. They are called as leaf nodes. They does not have any child. Tree is also a graph, as we have already been mentioned, and more on that. If I'm going to throw more light on that, visiting a vertex, it means going to a particular vertex or checking a vertex value. Exploration of vertex. These are the terms or these are the terminologies that may be used as that may be asked in gate examination. It means visiting all the adjacent vertices of an selected node, and traversing means passing through nodes in a specific order. In terms of level order, it is a traversing method where we have to visit every node on a level before going to the lower level. If I say layer 0, layer 1, and layer 2, I can visit layer 1 first, layer 0 first, all the nodes, those who are there in layer 0 can be visited. Then I'm going to come back to the layer 1 or level 1, whatever all the elements those who are present in layer 1 can be visited after that, and after that layer 2 will be get visited. The sequence should be from left to right itself. 0, a traditional one, 0, 1, 2, 3, 4, 5, 6, 7. That will be your output, or called it as the level order breakfast search. Breadth means the distance or the measurement from the side to side that of something, width or wideness or diameter that can, or range or extent. Breadth first search for a graph is similar to breadth first traversal of a tree, where we have to visit all the nodes, those who are connected in that layer or those who are connected adjacently. The only catch is here, unlike trees, graphs may contain cycle. So we may come to the same node again. To avoid processing, a node more than once. We are using Boolean visited array. Boolean means if we have visited that particular node, there is no any need to revisit that given node again. For example, in the following graph, we have started the traversal from the vertex 2. Then when we came to the vertex 0, we look for all the adjacent nodes of it. Where 2 is also an adjacent vertex of 0. In the given diagram, 2 is also the adjacent vertex of the node 0. If we don't mark visited vertices, then 2 will be proceed again. So we need to visited sorry we need to I mean we need to mark visited the the visited vertex, so that to avoid the cycle formation. So the level order of this given tree is 1, 2, 3, 4. Level means I already explained that level by level. Firstly, we are going to visit the all the nodes those who are in layer 1, layer 0. All the nodes those who are in layer 1, all the nodes those who are in layer 2, all the nodes those who are in layer 3 itself. So accordingly, the level order I can say like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. If I'm going to visit it in terms of breadth first search, the breadth first search for the given tree is exactly same. 1, the next 2, 3, 4, the next 5, 6, 7, 8, the next layer or next breadth. Breadth means the distance as we know or measurement that we are aware. 9, 10, 11, and 12. So I have mentioned both the level order and the breadth first search over there. How the illustration, see in the given diagram, with the help of these diagrams, I have explained you. I'm going to explain you how that BFS works. It is simply like the given graph is like this: 1, 2, 3, 4, 5, and 6, where we are going to point it out the visited node, and then we are going to enter it into the queue. The visited node is we are going to mark it with orange color, and unvisited will be the blue color. In the figure 1, we have initiated the illustration or we have initiated the process, and then we are visiting node number 1 first. Then I have visited one, then entered into the queue and then print. And that means out it from the queue. Then visited in the next figure number 4. I have visited node number 2 and 3. After removing one from the queue and printing it, we in-queue its non-visited adjacent nodes. The non-visited adjacent nodes of the node 1 are 2 and 3. So I have queue it in that particular part. But in the next step, I have printed it. So visited will be marked as 1 and unvisited will be marked as 0. And then I'm going to enter every element into the queue and then print it out from nodes from the queue to the print position. 1, 2, 3, 4, and 5 get printed and visited and printed from the queue. Ultimately, when we have visited all the nodes, all the diagram is completely in orange mode. Since I have already mentioned the visited node, we are going to change the color of that node, that is from blue to orange, and that's why I have mentioned it, and that's why I have given it. Accordingly, when BFS is just like a level order for it, it follows the three simple rules. The rules are very clear. Visit the adjacent unvisited vertex first, mark it as visited, insert it in a queue and display it. That's it. Rule number 1. Rule number 2. If no adjacent vertex is found, remove the first vertex from the queue. That if you don't found any adjacent vertex, remove the first vertex from the queue. Rule number 3 is repeat rule number 1 and 2 unless and until the queue is empty. Unless and until the queue is empty. Next, this is the diagrammatic representation of breadth first search. I can say like firstly the steps. Let's look at the details of how breadth first search works. Step number 2. If I started from A, I have mark and in queue A, insert the element A in the queue. Step number 2, I have withdrawn queue because I am going to print it. DQ. Step number 4 is like mark and in QC, mark visited and in QC, mark and in QE, DQC. See, both are the adjacent of A, E and C. So initially I have mark first and then DQC. After DQing C, I am mark and in Q B itself. Because there are three different adjacent nodes of C: B, D, and F. Then go by one. B is there, D is there, and F is there. I have included all the things. Then after visiting all the unvisited vertices of the node C, then I am going to DQ E, B, E, and F. Ultimately, step by step, the complete breadth first search is like this: A, C, E, B, D, F. Like this. Various applications of this breadth first search are like there are many applications of breadth first search. Let's discuss some of them. Where it's shortest path and minimum spanning tree for animated graph.
In an unweighted graph, the shortest path shortest path is the path with least number of edges. Or minimum cost spanning tree can also be able to draw it or to find it or to recognize it with the help of this breadth first search. With breadth first search, we always reach a vertex from a given source using the minimum number of edges, and it can also, in a case of unweighted graphs, any spanning tree is minimum if minimum spanning tree if when we are going to use it for breadth first search traversal for finding the spanning tree. Peer-to-peer networks are again like in your LAN connections, BitTorrent, breadth first search algorithm is used in terms of to find all the neighbor nodes. Whenever you are connected in terms of network or in terms of any networking, computer networking, majority that breadth first search or that minimum cost spanning tree or MST by applying say Kruskal's or by applying say Prim's algorithm to find the minimum cost of that spanning tree, all these connections are made possible. Ford Fulkerson method for computing the maximum flow in a flow network is again the exam applications of breadth first search. Crawlers in search engine, you can show that majoritarily if you are sequentially if you are searching anything, it can show you the related search that depends on the breadth first search algorithm. Depth first search can also be used over there in when we are going to deal with the depth first search. I can explain you all that things again, how that depth first search works. Social networking websites are again the application of breadth first search, and that GPS networking systems uh, where breadth first search is used to find all the neighboring locations. We are very much aware and very much used to about that GPS location. So navigation systems such as Google Maps, when we get directions to reach from one place to another using breadth first search, can be given over there. And again, of course, it again shows you the data set and the option and the path with the help of shortest path algorithm also. BFS is applied in the shortest route as is generated, which is used to give the directions or real-time navigations. Remember this thing, real-time navigations uh, are always using the shortest path. In social network, we can find the people within some distance, say K, from a person using breadth first search till K levels and it can be levels. Broadcasting in network as well as garbage collection, cycle detection in undirected graph, path finding are again the applications of that breadth first search. Time and space complexity for BFS is order of vertices plus edges. Where V is the number of nodes and E is the number of edges, and the space complexity that can be expressed with the help of order of V, where V is the cardinality for the set of vertices. This is all the conclusion of breadth first search itself, where breadth first search algorithm is now very important algorithm that traverse in the graph and breadthward motion. We have always find it out, and it follows the queue as a data structure. This is all about that breadth first search. Now we'll look into the depth first search, and up till the 2-3 minutes will be there for depth first search for the today's session. Depth first search is another popular graph search strategy where the idea is very similar to pre-order travel search. Visit the children first. Remember, visit the extreme children first, and DFS can provide the certain information about the graph that BFS cannot. Yes, DFS can provide you the information related to the graph, but BFS cannot give. Since we are in BFS, we are visiting the vertices in a layer by layer order or level by level order. It can tell whether you have countered, whether you have encountered a cycle or not. DFS is following that particular way. DFS will continue to visit the neighbors in a recursive pattern. Since whenever we have visited from the node V from visit V from U, we recursively visit all unvisited neighbors of V. By using V or backtracking, with the help of that backtracking, we can visit the other unvisited nodes from that V itself. It is possible that W2 was unvisited. When we recursively visit W1, that becomes visited. That time we return it from the recursive call. So from V, if I have visited V from U, I can repeat W1. I can again visit to V. then we'll reach to W2, again visit to V, and then we'll reach to W3. The recursive position V can be visited recursively but printed only once. I repeat, V can be visited recursively but printed only once. Like this is the normal algorithm for every vertex V. Flag vertices are not visited, and flag yourself as a visited. So flag V is equal to true for all the neighbors of W and V. So we can also find it by using the path predictions as well. So say if the 2 is the source in the given graph, so adjacency list is mentioned. There are whatever the nodes like 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Adjacency list mention the thing like the adjacent nodes of 0 are a is 8, 1 is 3, 2, 3, 7, 9, 2, 2. The adjacent nodes of the node 2 is are 8, 1, and 4. 3 are 4, 5, 1, 4 are 2 and 3, 5 are 3 and 6, 6 are 7 and 5, 7 is having 1 and 6, 8 is having 2, 0 and 9, and 9 is having 1 and 8. So initialize the visited table first and then visited the unvisited adjacent nodes in a depth first manner. So if source 2 is having the we have started it from source 2, then 8, then 9, then 1, then 3, then 3, then 4, back to 3. Since 3 is having two adjacent nodes with them, 3 is connected with 4 as well as 3 is also connected with 5. So back to 3, and from 3 again we are going to reach to 5. Then back to but then go back to 6, since 5 is having only one adjacent node, that is 6, and 3 is already been visited, and the only unvisited node which is at last, that is 7, will reach from 6 itself. So this is all about the track, and then it can be printed like this to get the final visited order. Time complexity of that first search is like order of n plus m, where the running time from DFS is proportional to the number of edges and number of vertices itself. So you will see the written as order of vertices plus edges will be the time complexity for the same. This may be the DFS tree. You can definitely able to solve all these things by using as a part of work or homework, I can say. So as a part of practice work. So this is all about the today's video. Thank you for your patience hearing. Over to you, Neeraj sir.
Yes, sir, I'm ending the broadcast. Thank you so much.
Yes.